Hello and good morning. What do you call a tooth in a glass of water? A 1 molar solution. That's actually pretty good. All right. I'm going to try to make this as quick as possible, but it's probably going to be relatively long. And don't speed it up just to get through it like somebody does at home. All right, we'll go over the homework. We'll do a quick recap about oxidation and reduction and oxidation and reducing agents. And then it's half reactions. Today, it's going to start to get a little hairy. Over the next week, it's going to get challenging, okay? So we're going to take it slow because we've got a little bit more time, and then we'll do some homework, all right? So, 3, and hopefully I can use green, okay. So, all the rules are up there. A fair number of people are getting these wrong. A lot of people had -4 here or -2. Remember, the rule is if you have an atom by itself, it's going to be 0. Even if it's combined with itself, that's 0. Okay? 10. S and HSO4. Okay, so SO4, I know, is a 2-. I remember that from my CRT. SO4 is 2-. So, -2 is my total here. So, 4 oxygens. I know 4 oxygens are -2. It's a -8. My total here is to be -1. Excuse me, -2. Because SO4 is a -2. Sulfur, there is 1 of them. This is my unknown. And -8 and -2, this has got to be a 6. 6 plus -8 is -2, so this is a 6. Try to remember to put your positives too, okay? You have to have this part down in order to do any of the rest. So this has to be done first. If it is an ion, you use the charge of the ion. That's pretty straightforward. 15, what else do we have to do? Number 20. Ion, use the charge of the ion. -1. 25 we did. 27, I think. Hydrogen and OH-. Well, here's oxygen, here's hydrogen. It's telling me that it has a -1 total. I've got 1 oxygen. I know each oxygen is -2. That's a -2. I've got 1 hydrogen. I don't know what that is, but my total has to be -1. So this has to be a +1. -2 and 1 is a -1. This must be 1. Okay? And lastly, number 30. If I can pull this up anymore, good. 30, carbon and C2O4 2-. So my total here is carbon, I've got oxygen, I've got 2 carbons, I've got 4 oxygens. I know each oxygen is a -2. Remember, there's only one exception with that, and that's peroxides, any of the peroxides. Usually peroxide, it's H2O2 really. Think about it, that's pretty much the only one where oxygen will be a -1. So -8, my total here is -2. This number here has to therefore be 6. And because of that, 6, 2 times what is 6? That's got to be 3. In this case, carbon is going to be a +3. Okay? You have to know how to run through those. Okay? So that's the homework. And let's run through a quick recap. Okay, so what you should know so far is oxidation is losing electrons to become more positive. Reduction is gaining of electrons to become more negative. Oxidation the mnemonic for that is LEO, loss of electrons, oxidation. Or it's oil, oxidation is losing, like oil rig, Leo ger. Reduction, oil rig, rig. Reduction is gaining, we're talking about electrons this whole time. And ger, as in Leo ger, gaining electrons is reduction. Okay? The other thing to recognize, to know, is whether it is a redox reaction or not. Essentially, if it's a double replacement reaction, it's not going to be a reduction, or excuse me, a redox reaction. If it's a single replacement, it's going to be. All right? A lot of times, if it's in a neutralization reaction between an acid and a base, it's also not a redox reaction. And lastly, you have to remember, so far, is that oxidizing agents are those things that get reduced. It's an agent because it causes the other thing to get oxidized, and vice versa. So if it's an oxidizing agent, it's the thing getting reduced. If it is a reducing agent, it is the thing that gets oxidized, and it causes the other thing to get reduced. Okay? So most acid-base reactions and double replacement are not redox reactions. Okay, so be able to recognize whether it is a redox reaction or not. Okay, so here's today. Today, it starts to get a little bit hairy. Okay, so please watch these videos. I'm going to suggest a couple other videos. They go into a little bit more detail than we need because I want to do it a little bit more step by step, but you'll get the basics of it. Okay, definition. Each chemical reaction can be separated into two reactions. We already know reduction, so the other one has to be oxidation. A half reaction shows either the oxidation or the reduction reaction and how the electrons, or following electrons, are gained or lost. So let's look at this redox reaction. I know it's a redox reaction because it's a single replacement. The zinc is going to kick out the hydrogen gas. When I add hydrochloric acid to zinc, you know that it's going to bubble. And we know that because of table J, the reactivity series. Zinc is above hydrogen. So what happens? Hydrogen gas is given off. So the first thing that I'm going to do is assign oxidation numbers. Any atom by itself is going to be 0. Any atom by itself, including bonded with another atom of the same element, is going to be 0. Okay. Hydrogen is either +1 or -1, and you can look that up in your CRT. And chlorine can be other things, but for the most part, it's going to be -1 when it's with hydrogen. Why? Because chlorine has a higher electronegativity. And since it has a higher electronegativity, by the way, it is right next to fluorine. Okay, it can be -1, +1, +5, +7. It has a much greater pull on electrons than does hydrogen, which is way over there. Okay. It's going to be a pain. Okay, so it's +1, 0, chlorine. Now zinc is 0 here by itself, but where do you think that 2 came from? That 2 came from zinc. Zinc has a +2. There we go. That'll make it easier. Zinc is right here, and it only has a +2. We have no choice, so that makes it easier. So zinc is a +2, and since I have 2 positives here, this must be a -1 because 2 times -1 is -2, and this has to be electrically neutral. So, look at chlorine. It's -1, -1. I think the other day I misspoke and said that that was called a bystander. It's called a spectator. My fault. It's called a spectator ion. Okay? I have a feeling we already did this. But Okay. Zinc goes from 0 to positive 2. So from this you can see that zinc has been what? So if it goes from 0 to positive 2, it must have lost electrons. It must have lost electrons because its electrons are negative, and in order to become more positive, you have to get rid of negatives. So if it is losing electrons, it is being oxidized. And since it has been oxidized, it must be the reducing agent, just to remind you. And hydrogen starts as a positive 1 and becomes 0, so its oxidation number has been reduced. So this is a reduction on that side. So what do I do? So now I can take each of the reactions, or this whole reaction, and split it into 2. Now, as I told you before, this chlorine is a spectator, so I don't have to include it in my half reactions. If you have a species that does not change its oxidation number, you don't have to include it in your half reactions. All right, so let's get down to it. So I start with zinc with a 0, and it becomes zinc 2 positive, as I showed here. And in order for me to have a balanced electrical charge, I've got 0 charge over here, I've got a positive 2 charge here, I have to balance that out. So in order for me to get a 0 over here, I put 2 electrons on the product side. So a positive 2 and a negative 2 equals 0. Okay? Positive 2, negative 2. So it has lost these electrons, and therefore this is the oxidation half. So I start with hydrogen, that's positive 1. It goes to 0, which is going down. Positive 1 to 0, it's getting reduced. This is showing the reduction. So the new piece here is that in order for both halves, both sides of the chemical equation to be electrically neutral, I have to add electrons on one side or the other. Okay? So positive 1, negative 1, that equals 0. Just like up here, this is 0. I have positive 2 charge, I need 2 electrons. Okay? Now, this is the first step, and we're going to take baby steps with this. Note, however, that the above reaction is not balanced. Look, I've got 2 electrons up here and only 1 here. We'll take care of that toward the end of the week. When balancing half reactions, the number of atoms and the number of electrons must be balanced. We have to keep that in mind. So let's try these. All right? So we're going to start with ammonia. This first one here is the Haber process, in which we take nitrogen gas, hydrogen gas, and make ammonia. All right, so the first thing I'm going to do is assign oxidation numbers. Any atom by itself, or even bound to itself, is a 0. Any atom bound to itself, 0. Okay, now what about this? Well, you know that that 3 came from nitrogen, and you know that hydrogen can only have one of 2 oxidation numbers. It's either positive 1 or negative 1. So how do I decide? Well, in this case, I have to figure out which of these 2 elements is more electronegative. So let's look. Here's nitrogen. Look at them all. There are 8 different oxidation states. Look how close it is to fluorine, however. So nitrogen is pretty electronegative compared to hydrogen, which is here. Okay? So if we looked up the electronegativity of nitrogen and compared it to hydrogen, this is more electronegative. So what does that mean? that means it's going to grab the electrons from hydrogen. So that 3 comes from nitrogen, and since it's more electronegative, it's negative. So this is a positive. So I've got 3 positives here, 3 negatives here. Don't worry about the coefficients right now. Okay, the coefficients are there only to balance the whole thing out. Okay, so we're going to take baby steps. So positive 3, negative 3. So now I'm going to split it into 2 half reactions. I'm going to start with nitrogen. Now, normally, if I have an atom inside of a molecule, I don't include this. But if it's a diatomic molecule, like this and this, I'm going to keep that nitrogen 2. I'm going to keep the 2 for the nitrogen there. The oxidation number is 0. And then I've got nitrogen here. It is a negative 3. And I have to, just because of this diatomic thing, this 2 has to come over here. Now that's specific to the diatomic ones. Okay, so what's my charge? I've got 0 over here. I've got negative 3, but I've got 2 of them. That's a negative 6. So 0, negative 6. How do I balance this out? If I put 6 electrons over here, the total on this side is going to be negative 12. So I'm going to put 6 electrons in this side. Now I've got 6 negative charges on the reactant side and 6 negative charges on the positive side. This is balanced. Is this oxidation or reduction? Look at the oxidation number. Did it go up or down? It went from 0 to negative 3. It got reduced. That's one way to think of it. The other way to think of it is GER, gaining of electrons. The nitrogen gas is gaining electrons. They're getting added. And that's reduction. Okay? Second part, I've got hydrogen here. Just like the nitrogen, it's a diatomic, so I'm going to leave the 2 there. This is a 0. Hydrogen here, I'm going to erase this because this is a little confusing. Let's get this out of the way. So down here, I've got hydrogen, which is a positive 1. Same thing, since I've got a 2 here, I have to have a 2 here. That's a 2. So, on the left side, I've got a electrical charge of 0. On the right side, I've got a positive 2. Positive 1, there are 2 of them, that's a positive 2. How do I balance this out? If I put a negative 2 over here, that means that would be a positive 2 here. So I want both of these to have 0. Okay? So 0 here, positive 2 and negative 2, and that's going to be canceled out as well. So the hydrogen has lost electrons, it has gotten oxidized. Okay? So this is the first step. After this, as we go on, we have to balance that out and it gets complicated. All right, so let's switch colors. Let's try to switch colors. Let's try this one. Okay, I'm going to start with giving the oxidation number. Well, I know this one's 0. Okay, S and O2. Well, I can do that over here. S and O2. Don't worry about the coefficient. Sulfur, there's 1 of them. Oxygen, there are 2 of them. It's negative 2. I don't know what that is. That's negative 4. This is a molecule, so this total is 0. And this must be 4. 4 plus negative 4 is 0. That's a 4. So this is a positive 4. I'm going to change to blue. This is positive 4. Doesn't matter what pen I use, I guess, huh? Positive 4, and oxygen is negative 2. All right, let's go over here. Same thing, kind of. So SO. There are 3 oxygens in 1. Sulfur, 3 times negative 2 is negative 6. This is a molecule, therefore it is electrically neutral. So what has to go here? That's a positive 6. I put a 0 here. There's 1 sulfur. So this is a 6, and it's a positive 6. So this is positive 6, and this is negative 2 again. Okay. Positive 4 to positive 6. Let's take the sulfur first. Now, I don't worry about the coefficient right here yet. Okay? So I've got sulfur, and it's a positive 4. I've got sulfur over here, it's a positive 6. What do you think I should do? Well, if I put the electrons on this side, it would make this negative 2, and then it wouldn't be balanced. So I need to reduce this by putting 2 electrons on that side. So sulfur is a positive 6. 2 electrons, take that away, that's a positive 4, positive 4. Is this gaining or losing? Is this an oxidation or reduction? Well, the oxidation number goes up, and it has lost the electrons. So this is an oxidation. So what do we have down here? O2. Now remember, this is a diatomic atom, so I'm going to leave the 2. I've got oxygen here. I'm going to take that 2 and bring it here, just like I did up there. This is 0, and this is negative 2. So 2, 0 to negative 2, the oxidation number has reduced, it has gone down. So this is the reduction half. And what do I have here? Negative 2 times 2 is a negative 4. This is 0. So I need to add 4 electrons to this side. So now I have a negative 4 charge here, negative 4 here. Now I'm balanced. Okay? Now you can see that I've got negative 4 electrons here and 2 electrons here. So we're not quite there as far as the full thing. But that's it. All right? Let's look at your homework. 1 through 5 only on this sheet. Okay, it's in your packet. Just through here. Don't worry about the review. All right? It's basically assigning oxidation numbers. Good luck.